Okay, let's go. Number 1. WR 104. There is a star in the constellation Sagittarius that is going to die. Not today. Not in any human lifetime. But the star, designated WR 104, is a Wolf-Rayet binary system, a star that has already burned through the hydrogen and helium that fuel most stars, and is now consuming its core's heavier elements in a process so energetically violent that it will end in one of the most powerful explosions in the known universe. When WR 104 goes supernova, it may produce a gamma-ray burst, a focused beam of radiation containing more energy than the Sun will emit across its entire 10 billion-year lifetime, compressed into two jets and fired outward from the star's poles. One of those poles may be pointed at Earth. Gamma-ray bursts are the most energetic electromagnetic events ever observed in the universe. The beams are extremely focused, typically just a few degrees wide, which means most supernovae fire their gamma-ray bursts harmlessly into empty space. But when a burst is aimed at an inhabited planet within the right distance, the consequences are immediate. A gamma-ray burst originating within 6,000 to 8,000 light-years of Earth, with its beam aligned in our direction, could destroy 25 to 50% of Earth's ozone layer within seconds. Without ozone, ultraviolet radiation from the Sun reaches the surface at lethal intensity. Phytoplankton, which produce more than half of Earth's oxygen and anchor the marine food chain, would collapse. Agricultural productivity would fall. The cascading extinction would take decades to fully unfold. It is not a fast death, it is a slow one. WR 104 was first identified in 1998 by Peter Tuthill at the University of Sydney, who observed its distinctive pinwheel nebula, a spiral structure created by the interaction of the binary star's solar winds. Distance, approximately 8,000 light-years from Earth in the direction of the galactic center. The Wolf-Rayet component, estimated at approximately 25 solar masses. The star's rotation axis, inferred from the geometry of the pinwheel nebula, appears to point roughly toward Earth. A 2008 spectroscopic analysis by Grant Hill and colleagues estimated the alignment within approximately 16 degrees of pointing directly at Earth. The estimated kill zone, the angular range within which a planet receives a lethal gamma-ray burst dose, is roughly 5 to 10 degrees. WR 104 could go supernova any time from now to approximately 500,000 years in the future. Gamma-ray burst researchers note that the estimated 16-degree misalignment places Earth outside the most dangerous zone. Not all Wolf-Rayet supernovae produce long-duration gamma-ray bursts. Only about 1 to 2% generate the collapsar-type burst, most dangerous at this distance. The distance of 8,000 light-years is at the outer edge of serious concern. The situation is monitored by the scientific community. But the 16-degree offset was estimated from spectroscopic data with acknowledged measurement uncertainties. A 2021 review of WR 104 noted that the true error bars on the alignment are larger than initially presented, meaning Earth could be anywhere from comfortably outside to directly within the beam's path. This matters in a way no mainstream reassurance adequately addresses. Light and radiation travel at the same speed. If WR 104 has already exploded, the gamma-ray burst is already in transit. If it is aimed at Earth, there will be no warning. None at all. The Fermi Gamma-Ray Space Telescope would register the event and the arrival simultaneously. Warning and impact are the same moment. If WR 104 detonated 7,999 years ago, the burst arrives in approximately 1 year. The decision was already made by physics, approximately 8,000 years ago, 4,700 years before recorded human history began. Could WR 104 produce a dangerous gamma-ray burst even if its axis is slightly off direct alignment? What true margin of error exists in the 2008 spectroscopic alignment measurements? How many other Wolf-Rayet systems within the 8,000 light-year danger radius have been examined for alignment with Earth? And what would any institution actually do with 1 hour of warning? From a star 8,000 light-years away whose next act may already be in transit, we turn to something much closer, a 490-meter asteroid with a specific probability number in NASA's own records, and approximately 150 years to decide what to do about it. Maybe. Number 2. Bennu. Imagine a September evening in the year 2135. The world is not so different from ours. Cities, technology, lives being lived without alarm. Then astronomers confirm what computer models have been quietly indicating for over a century. A 490-meter asteroid may be on an impact trajectory with Earth, sometime between 2175 and 2199. There will be time to respond. The engineers who must execute the deflection mission, however, have not yet been born. Neither have their parents. And the institutions charged with building and launching the spacecraft depend on the political will of governments that do not yet exist. The asteroid is called Bennu, and NASA has studied it more closely than any other potentially hazardous asteroid in history. OSIRIS-REx launched September 8, 2016, entered Bennu's orbit in December 2018, and descended to the asteroid's surface on October 20, 2020, to collect a sample. The return capsule landed on September 24, 2023, delivering 121.6 grams of pristine asteroid material, the largest sample ever returned from an asteroid. Scientists studying the material confirmed that Bennu is a rubble pile, an aggregate of loosely consolidated rock and debris held together by gravity, not a single solid body, dating to the formation of the early solar system approximately 4.5 billion years ago. Bennu diameter, 490 meters. Mass, approximately 73.5 billion kilograms. Orbital period, 436.6 days. Classification: B-type carbonaceous asteroid. Impact probability between 2175 and 2199, 1 in 1,750, or 0.057%. The highest confirmed impact probability for any known asteroid of this size in current catalogs. Impact energy, if direct collision occurs. Approximately 1,200 megatons of TNT, equivalent to roughly 80,000 Hiroshima bombs. A 2023 study using OSIRIS-REx trajectory data identified 26 distinct impact scenarios between 2175 and 2199, with September 24, 2182, carrying the highest individual probability. Planetary defense scientists explain that 0.057% is an extremely small probability, and 150 or more years of lead time is more than sufficient for effective deflection. NASA's DART mission in September 2022 demonstrated that a kinetic impactor can alter an asteroid's orbit, reducing Dimorphos's orbital period by 32 minutes, far exceeding the minimum needed. Scaled deflection of Bennu with appropriate lead time is technically achievable. The situation is being monitored, but this requires a chain to hold for 150 years. Bennu's trajectory is affected by the Yarkovsky effect, requiring continuous, precise monitoring across a century-plus timescale. The 26 identified impact scenarios carry uncertainties that compound with every decade. And rubble pile asteroids respond to kinetic deflection differently than solid rock. A kinetic impactor striking a loosely bound aggregate may simply push the debris apart rather than deflecting the whole object cleanly. DART targeted Dimorphos, a small moon of a larger asteroid, a fundamentally different configuration than a primary body like Bennu. No one has tested deflection on a rubble pile primary body. There is also a question no orbital mechanics equation can answer. If the critical decision point for authorizing a Bennu deflection mission arrives during a period of geopolitical instability or institutional breakdown, who acts? What legal framework compels it? What budget line in what government funds it on a 150-year maintenance schedule? Who is legally accountable for ensuring that decision occurs at the correct moment, one that may fall 80 to 120 years from now? If Yarkovsky measurements need revision in 2080 and the revised probability jumps significantly, what mechanisms exist to authorize an emergency response? How confident are current models that a rubble pile primary body responds to kinetic deflection the way Dimorphos did? And which civilization, on which version of Earth, is actually making that call? From an asteroid with a century and a half of warning, we turn to one with a specific date already on the calendar, April 13th, 2029, 3 years away, and it will be visible to the naked eye. Number 3. Apophis. The year is April 13th, 2029. You are standing in a field somewhere over Europe when you notice something in the sky that does not belong. not the moon, not a plane. A point of light moving with visible, deliberate speed across the darkness, bright enough to track with the naked eye, brighter than most stars. People around you have their phones out, some are silent. You are watching a 340-meter asteroid graze past Earth at a distance closer than the satellites carrying your GPS signal. You are watching Apophis. Named after the Egyptian god of chaos and destruction, 99,942, Apophis earned its title before anyone saw it clearly. When astronomers Roy Tucker, David Tholen, and Fabrizio Bernardi first calculated its trajectory in December 2004, they assigned it a 2.7% probability of striking Earth on April 13, 2029. For 72 hours, it held the highest impact probability ever recorded for an object of its size. The planetary defense community held its breath. Additional observations refined the orbit and ruled the 2029 impact out, but the flyby is still coming. And it is unlike anything in recorded human history. NASA has confirmed Apophis will pass within 31,160 kilometers of Earth on April 13, 2029. Geostationary satellites orbit at 35,786 kilometers. Apophis will pass inside that ring. The asteroid is 340 meters wide, roughly the footprint of the Empire State Building, traveling at 7.4 kilometers per second. It will be visible to the naked eye over Europe, Africa, and parts of Asia, moving across the sky like a fast-moving star. No asteroid this large has ever passed this close to Earth in recorded history. First detected June 19, 2004, by Tucker, Tholen, and Bernardi at Kitt Peak National Observatory, named 99,942 Apophis after the Egyptian deity of chaos. Initial impact probability, 2.7%. Torino scale level 4, the highest any near-Earth object has ever reached. Confirmed closest approach, 31,160 kilometers. Geostationary orbit, 35,786 kilometers. Apophis passes inside that boundary. Diameter, 340 meters. Impact energy if direct strike, approximately 1,717 megatons of TNT, more than 34 Tsar bombas, the largest nuclear weapon ever detonated. Radar observations in March 2021 ruled out the 2029 and 2036 impact scenarios. No significant impact probability exists for the next 100 years. Planetary scientists explain that the 2029 flyby poses no impact threat and represents an extraordinary scientific opportunity. The extreme proximity will allow observation of how Earth's gravity reshapes the asteroid, alters its rotation, and potentially triggers surface landslides. This is a once-in-a-century opportunity, not a threat, but this explanation requires trusting every variable in the model. Apophis's trajectory is affected by the Yarkovsky effect, the slight but real push an asteroid receives as it absorbs sunlight on one side and radiates heat from the other. This force accumulates over years and decades. The Yarkovsky effect for Apophis has already shifted the impact probability estimates multiple times. Planetary defense scientists use the concept of gravitational keyholes, specific regions of space that, if an asteroid passes through during a close approach, will redirect it toward Earth in a future encounter. During the 2029 flyby, Apophis will pass through a region where multiple potential keyholes have been identified. Earth's gravity will do the redirecting. We will not. What happens if the Yarkovsky measurements contain undiscovered errors? If Apophis drifts through a keyhole that current calculations have not precisely mapped? How many other asteroids exist in similar orbits that have not yet been found? And if a 340-meter object can approach this close without triggering global emergency protocols, what does that reveal about our actual level of preparedness? From the god of chaos crossing our sky, we turn to a different kind of threat, one that travels at the speed of light and can kill every satellite in orbit before a single alarm sounds. Number 4. The Solar Storm. The date is July 23, 2012. You are going about your day, completely unaware that a wall of magnetized plasma the size of several Earths has just erupted from the Sun. It is traveling at 2,500 kilometers per second. It will reach Earth's orbital path in approximately 17 hours. In 9 days, Earth itself will be in that exact location in space. But today, July 23rd, you are fine. Your power is on. Your phone works. Your car starts. 9 days later, Earth will be fine too, because 9 days earlier, you weren't there. In July 2012, an extreme solar coronal mass ejection erupted from the Sun with an intensity, scientists later confirmed, matched the 1859 Carrington event, the most powerful solar storm in recorded history. The Carrington event knocked out telegraph systems across North America and Europe, set telegraph paper on fire, and sent uninvited electrical current through lines that had no power source. That was 1859, when global electrical infrastructure meant telegraph wires. In 2012, it meant power grids serving billions of people, financial systems running entirely on electronic transfers, GPS satellites guiding aviation and shipping, and internet infrastructure connecting every major economy on Earth. The storm missed all of it by 9 days. The July 23, 2012 event was recorded by NASA's Stereo A spacecraft. Analysis published in 2013 and 2014 by scientists at UC Berkeley and NASA Goddard confirmed the intensity matched or exceeded the 1859 Carrington event. Solar wind speed, 2,500 kilometers per second, nearly 4 times typical velocity. A July 19th CME had cleared a path through dense solar wind, allowing the following burst to maintain full intensity across the full distance to Earth's orbit. A 2014 study by physicist Pete Riley, published in Space Weather Journal, estimated the probability of a Carrington-level event hitting Earth in any 10-year period at approximately 12%. Solar Cycle 25, the current solar cycle, exceeded NASA's initial predictions. Sunspot counts hit 40-year highs in 2024. Solar physicists explain that the Sun's approximately 11-year activity cycles are well understood, and the 2012 storm, while extreme, was a statistically rare event for its cycle. NASA's Discover satellite, positioned at the lone Lagrange point between Earth and the Sun, provides roughly 15 to 60 minutes of warning before CME impact. NOAA operates contingency plans for space weather events, and some utilities have begun hardening systems. The situation is monitored, but 15 to 60 minutes of warning is the whole window. Discover sits 1.5 million kilometers from Earth. ACME, at 2,500 kilometers per second, reaches Discover in about 10 minutes. Then Earth, 15 minutes after that. 25 minutes for a civilization that has never experienced a modern Carrington-level event. A 2008 report commissioned by NASA estimated that a Carrington-level storm today would collapse power grids across North America, Europe, and Australia within hours. Recovery, 4 to 10 years. Cost in the first year alone, $1 to $2 trillion, with cascading failures in water treatment, food distribution, and medical systems within the first week. The 2012 storm was more powerful than typical Carrington modeling suggests. It hit a region of space we had already passed through 9 days before. How confident are we that current grid hardening matches what 2012 nearly delivered? If Discover fails during an active storm, what does warning actually look like then? What fraction of the critical infrastructure that would need to stay online has actually been shielded? And if the storm arrives at 3 a.m. on a Tuesday? From a storm that missed Earth by 9 days, we move to a disaster that did not miss one that humans triggered themselves, and that may already be past the point of stopping. Number 5. Kessler Syndrome. The year is 2009. You are working a console at the Joint Space Operations Center in Vandenberg Air Force Base, California, when the alarms go off. 2 satellites have just collided in low Earth orbit. Iridium 33, an active commercial communications satellite, has struck Cosmos 2251, a defunct Russian military satellite, at a closing speed of approximately 11.7 kilometers per second. The debris cloud begins expanding immediately. Within hours, what was 2 satellites is now more than 2,000 trackable pieces and hundreds of thousands of fragments too small to track and large enough to punch through a spacecraft hull. That was not the beginning of the problem. It may have been a symptom of one already underway. Donald Kessler, a NASA scientist, published a foundational paper in 1978 describing a scenario in which the density of objects in low Earth orbit reaches a point where collisions generate more debris than atmospheric drag can clear. Each collision creates more debris. Each piece risks further collisions. The cascade grows. Eventually, specific orbital shells could become impassable for centuries, sealing humanity below a permanent barrier of orbiting shrapnel. Even if every nation stopped launching satellites tomorrow, the existing debris would continue generating new debris through mutual collisions. This is the Kessler syndrome, and it does not require a single catastrophic event to begin. It only requires the generation rate to exceed the clearance rate. The 2009 Iridium Cosmos collision was the first confirmed accidental satellite collision in history. In January 2007, China tested an anti-satellite weapon on its own, Fengyun 1C satellite, at 865 kilometers altitude, creating approximately 3,000 trackable pieces and over 150,000 fragments, larger than 1 centimeter. At that altitude, atmospheric drag will not clear debris for decades to centuries. ESA's annual Space Environment Report for 2023. More than 36,500 trackable objects in orbit larger than 10 centimeters, plus approximately 1 million between 1 and 10 centimeters, plus over 130 million smaller than 1 centimeter. The International Space Station now performs several debris avoidance maneuvers per year. In November 2021, a Russian ASAT test forced ISS crew to shelter in docked spacecraft 4 times in a single day. SpaceX had over 6,000 Starlink satellites in low Earth orbit as of 2024, with approval for up to 42,000. Orbital debris researchers explain that the situation is serious, but manageable with international cooperation and active debris removal. Technologies including drag sails, laser ablation, and robotic capture are in development. ESA's Clear Space One mission, targeting 2026, will attempt to retrieve a defunct satellite for the first time. International guidelines calling for satellite deorbit within 25 years of end of mission are increasingly adopted. The system is stressed but not broken. But ESA's own simulation tools, Master and Delta, show that specific orbital shells between 700 and 1,000 kilometers are already at or near the critical density threshold for self-sustaining cascade. The 25-year deorbit guideline is a recommendation, not a law. Compliance rates remain incomplete. China's 2007 ASAT debris will be in orbit for decades, continuing to generate secondary collisions. A fragment 1 centimeter in diameter, traveling at orbital velocity, carries the kinetic energy of a bowling ball hurled at 300 miles per hour. The ISS crew works every day knowing that no tracking system covers objects smaller than 10 centimeters. A fragment they cannot see is statistically the most likely thing to kill them. The ISS has performed over 30 debris avoidance maneuvers since 2009. How close are the most congested orbital shells to the self-sustaining cascade threshold right now? What percentage of active satellites are capable of maneuvering at all if debris requires evasion? If the cascade begins in earnest, how long before GPS, weather forecasting, and communications satellites fail? And if that happens, how does anyone launch anything to repair it? From debris already circling above us, we turn to a threat that returns to the inner solar system every 130 years like clockwork and is 26 kilometers wide. Number 6. 109P/Swift-Tuttle. Every August, Earth passes through the tail of a comet. You have probably seen it. The Perseid meteor shower dozens of shooting stars per hour, burning up in the upper atmosphere, is Earth plowing through a river of debris left behind by a comet on its regular journey around the Sun. The comet is called 109P/Swift-Tuttle. You may not have heard its name the way you have heard Halley's or Hale-Bopp. You should have. Swift-Tuttle is 26 kilometers wide. The asteroid that ended the Cretaceous period and killed approximately 75% of all species on Earth was roughly 10 to 15 kilometers wide. Swift-Tuttle is nearly twice that. It comes back every 130 years, and the orbital math that says it will not hit Earth has a confidence window measured in centuries, not millennia. The Perseids exist because Earth's orbit intersects the debris trail Swift-Tuttle leaves in its wake. Every grain of dust burning overhead during August is a fragment of that comet's tail, vaporizing at approximately 59 kilometers per second. Swift-Tuttle itself last passed through the inner solar system in 1992, reaching perihelion, its closest point to the Sun, on December 12th of that year. That 1992 pass was the closest Swift-Tuttle had come to Earth in approximately 1,000 years. It will next return in approximately August 2126. Discovered independently on August 16, 1862, by Lewis Swift, and 3 days later by Horace Tuttle. Orbital period, approximately 130.1 years. Nucleus diameter, approximately 26 kilometers. Surface albedo, 0.04, one of the darkest surfaces in the solar system. Encounter velocity if impact occurred, approximately 59 kilometers per second. Impact energy, approximately 27 to 30 times the estimated energy release of the Chicxulub impactor. In 1992, astronomer Brian Marsden calculated a potential 1 in 10,000 probability of impact in 2126, briefly making Swift-Tuttle the most dangerous known object in the solar system at the time. Refined orbital data subsequently ruled out the 2126 impact. Current models show no impact risk for at least the next 2,000 years. Astronomers explain that Swift-Tuttle's orbit is now well characterized from multiple observed returns, and current solutions carry sufficient precision to rule out impacts for the foreseeable future. The 2126 close approach will be an observational opportunity, not a threat. The Marsden 1992 warning was a temporary consequence of limited data, quickly corrected by better observations. But comets are fundamentally harder to track than asteroids. They exhibit non-gravitational forces. Outgassing from their sunlit surfaces creates thrust that gradually shifts the orbital path over time. It is the same mechanism identified in dark comets. Swift-Tuttle's non-gravitational parameters have been measured from approximately 160 years of reliable modern observation, but projecting those parameters forward with confidence over multiple centuries requires assuming the outgassing behavior remains consistent. It may not. The 1992 Marsden warning was based on the best orbital data available and initially flagged a real concern before additional observations resolved it. That sequence is the same sequence that has characterized every high-profile asteroid and comet risk assessment in the modern era: initial calculation, concern, more data, revised reassurance. And Swift-Tuttle is 26 kilometers wide. There is no deflection technology on Earth capable of moving an object that large. Not DART, which moved a 160-meter moon. Not any nuclear option under study. A 26-kilometer impactor traveling at 59 kilometers per second is not a planetary defense problem. It is a geological event, a restructuring of the biosphere, the kind of thing that appears in the fossil record as a hard line. If non-gravitational forces shift Swift-Tuttle's orbit by even a few hundred kilometers over the next 130 years, how does that change the geometry of the 2126 close approach? What would a 26-kilometer impactor at 59 kilometers per second actually do to Earth's oceans and atmosphere? And every August, when you watch the Perseids and someone tells you to make a wish, you are watching debris from the most dangerous periodic comet in the solar system. From the comet behind Earth's most celebrated annual meteor shower, we move to the detection gap that allows threats like this to approach undetected until they are already past. Number 7. 2016 GO20. The astronomers almost missed it. In the summer of 2016, an object designated 2016 GO20 crossed through the inner solar system. It had no glowing coma, the cloud of dust and gas that forms around an active comet as solar heat vaporizes its surface. It had no visible tail. To every optical telescope and detection algorithm trained to identify comets by their most obvious characteristics, it appeared to be an ordinary asteroid. But it was not moving like an asteroid. The numbers did not fit. Something was pushing it. A comet's path through the solar system follows predictable gravitational curves governed by 3 centuries of verified mathematics. Active comets deviate from these curves through outgassing volatile material erupting from the surface as sunlight heats it, creating a tiny but measurable thrust. By tracking this deviation, scientists can infer outgassing even when they cannot see it directly. The object 2016 GO20 showed non-gravitational acceleration consistent with significant outgassing. It showed none of the visible signatures. It was a comet that looked exactly like an asteroid. Scientists had a name for what it was. They just had not confirmed the category existed yet. A 2023 paper published in Nature Astronomy by researchers including Daryl Seligman and David Farnokia identified 7 confirmed dark comets in the historical record. 1998, KY, 26, 2003 RM, 2005 VL, 1, 2010 VL 65, 2016 GO 20, 2010 RF 12, and 2006 RH 120. These objects exhibited non-gravitational acceleration approximately 100 times greater than typical asteroid behavior, while remaining visually indistinguishable from asteroids in all standard survey data. They range from approximately 6 to 800 meters in diameter. Oumuamua, the interstellar object detected in 2017, is now considered a possible 8th. Current near-Earth object surveys, Catalina Sky Survey, Pan-STARRS, Atlas detect dark comets only when their trajectories bring them close enough to observe as asteroids, with no automated alert that the trajectory prediction may be seriously wrong. Planetary defense scientists explain that the 7 confirmed dark comets were all relatively small and pose no immediate threat. Dark comets reflect light and are detectable by existing surveys when close enough. The primary complication is trajectory accuracy, not visibility. Algorithm refinement and long baseline tracking can account for non-gravitational forces once an object is suspected. The risk is manageable, but trajectory prediction is precisely the issue. When an asteroid is designated as potentially hazardous, planetary defense scientists calculate its Earth impact probability from its observed orbit. If that orbit includes non-gravitational forces, 100 times normal asteroid-level forces that are invisible because the object shows no outgassing signatures, the calculated impact probability is wrong. The actual trajectory diverges from the prediction over days and weeks. All 7 confirmed dark comets were identified retrospectively through analysis of orbital anomalies that only became apparent after long observation baselines had accumulated. If a dark comet of 400 meters or larger were approaching Earth on a threatening trajectory today, the impact probability in the database could be substantially incorrect. We would not know it was a comet. We would not know the trajectory was unreliable. It would sit in the catalog, unworried about, under a designation that said, Asteroid, no significant threat. How many objects in current near-Earth asteroid catalogs are actually dark comets with inaccurate trajectory predictions? What fraction of potentially hazardous candidates have received the long baseline tracking needed to detect subtle non-gravitational forces? If a dark comet were on an impact trajectory with 2 months of lead time, how would unmodeled outgassing change the deflection calculation, and what does a deflection mission look like on 2 months' notice? And how many objects in the database we use for planetary defense are not what we think they are? From objects that hide in plain sight, we turn to a star, visible to the naked eye every winter night, one already in the final stages of its life, and whose interior no instrument on Earth can read. Number 8. Betelgeuse. Find Orion on a clear winter night. Find the 3 stars of the belt. Look to the upper left shoulder of the constellation. That reddish point of light, brighter than almost anything else in the sky, is Betelgeuse. Your eyes process it as a point. It is not a point. If you placed Betelgeuse where our sun sits, it would swallow everything out to and past the orbit of Jupiter. It is a red supergiant, more than 700 times the diameter of our sun, burning at a surface temperature of 3,600 Kelvin compared to the sun's 5,778 Kelvin, and it is already dying. Between October 2019 and February 2020, Betelgeuse dimmed to the lowest brightness recorded in modern observation. The astronomical community watched closely. Some researchers circulated quiet papers about possible supernova precursor activity. Then the star rebounded. Analysis using Hubble Space Telescope and Herschel Space Observatory data, published in 2022, identified the cause. A massive surface ejection had expelled a cloud of stellar material, equivalent to 2 to 4 times the mass of the Moon, which condensed into dust and blocked the star's light from reaching Earth. It was not an imminent supernova precursor, but it was behavior that stellar evolution models had not predicted, and the star will explode. That is not in dispute. Betelgeuse is designated Alpha Orionis, spectral class M2 IAB. ALMA radio telescope array parallax measurements Place the distance between 530 and 700 light-years. Current mass, approximately 10 to 20 solar masses, reduced from an estimated 16 to 20 solar masses at formation. The Great Dimming lasted from October 2019 to approximately February 2020, reducing brightness to roughly 40% of normal. A 2023 modeling study placed Betelgeuse in the carbon-burning phase of stellar evolution, extending the estimated explosion timeline to 10,000 to 100,000 years. Minimum safe distance for a supernova to pose mass casualty risk on Earth, approximately 50 light-years. Betelgeuse, at 530 to 700 light-years, will not cause extinction. When it explodes, it will be visible in daylight for weeks, cast shadows at night, and send a neutrino pulse through Earth hours before the visible light arrives. Astronomers explain that Betelgeuse's supernova poses no extinction-level threat. The distance provides substantial protection, and modern neutrino observatories such as Super Kamiokande would detect the neutrino burst in advance of visible light, providing warning. The Great Dimming was explained by physical processes within the known behavior of red supergiants. The timeline has been extended. The situation is monitored. But the models that extended the timeline are the same models that did not predict the Great Dimming. The interior of a dying red supergiant is opaque to electromagnetic observation. Monitoring the internal burning stages directly requires neutrino detection sensitivity that current instruments cannot achieve at 700 light-years. They detect a supernova in real time, but cannot read the pre-explosion neutrino signatures of a star at this distance, years in advance. The 2023 carbon-burning estimate extended the timeline, but the same study acknowledged that the transition from carbon burning to the oxygen and silicon burning stages immediately preceding core collapse can take anywhere from a few years to millennia. We cannot observe which stage is occurring inside Betelgeuse right now. The 2019 surface ejection expelled material equivalent to 2 to 4 lunar masses in a single event, the most powerful surface ejection ever observed from a star at this distance. Betelgeuse is behaving in ways not anticipated by its models. At 700 light-years, a supernova would deliver measurable ultraviolet increases to Earth's surface over the following years, contributing to ozone depletion and elevated cancer rates in ecosystems already under environmental stress. Whatever is happening on Betelgeuse tonight, we will not know for 700 years. The light reaching our eyes right now left that star around the time of the Black Death. If it has already gone supernova, the light is already traveling toward us. There is nothing to do but look at that reddish shoulder of Orion and wait. Could Betelgeuse detonate on a timescale of decades rather than millennia? What fraction of Earth's ozone would a supernova at 700 light-years remove over the subsequent decade? And what does it mean that a star can change fundamentally and we will not know for 700 years? From a dying star 700 light-years away, we turn to a problem much closer to home, one operating in the literal blind spot of every telescope currently watching for threats from space. Number 9, 2023NT1. The discovery was announced quietly, almost as an afterthought. On July 4, 2023, astronomers at the Asteroid Terrestrial Impact Last Alert System, ATLAS, detected a near-Earth object and designated it 2023NT1. Routine calculations followed. The object was approximately 60 meters in diameter, large enough to level a major city if it struck an urban area. The astronomers determined that 2023NT1 had already passed Earth 2 days earlier, on July 2nd, at a distance of approximately 62,000 kilometers, closer than many operational satellites. No warning had been issued, because none was possible. The asteroid had approached from the direction of the Sun, placing it in a region of sky that no ground-based telescope can observe, even in principle. This was not an anomaly. It was a demonstration of a permanent, unavoidable gap in every detection system humanity currently operates. The geometry is simple, and the problem is insoluble with ground-based instruments. Earth orbits the Sun. Any asteroid whose trajectory brings it toward Earth from the sunward side will spend weeks or months in the area of sky dominated by the Sun's glare. Ground-based surveys operate primarily at night. Space-based telescopes in Earth orbit face the same problem. The Chelyabinsk meteor, which exploded over Russia on February 15, 2013, with the energy of approximately 500 kilotons of TNT, injuring more than 1,600 people and damaging buildings across 6 Russian cities, approached from the direction of the Sun. It was completely undetected until atmospheric entry. That object was approximately 20 meters in diameter, 2023 NT. One was 3 times wider and 8 times the volume. Asteroid 2023 NT. One discovered July 4, 2023, by Atlas Telescope in Chile. Closest approach, July 2, 2023, at 62,000 kilometers. Diameter, estimated 40 to 100 meters. Approached from within the solar exclusion zone, the region of sky permanently inaccessible to ground-based optical telescopes. Chelyabinsk impactor, approximately 20 meters diameter, February 15, 2013. Energy, approximately 500 kilotons. Injuries, 1,613. Damage across 6 Russian regions, also from the sunward direction, undetected until impact. Asteroid 2019, OK, approximately 100 meters, passed Earth at 70,400 kilometers on July 25, 2019, with roughly 24 hours of advance warning, also from the sunward direction. NASA's current estimate for discovered potentially hazardous asteroids larger than 140 meters, approximately 95%. For objects between 50 and 140 meters, estimated less than 40% discovered. The majority of the uncharted population occupies sun-crossing orbits. Planetary defense researchers acknowledge the blind spot as a significant gap. NASA's Near-Earth Object Surveyor, NEO Surveyor, is a space-based infrared telescope designed to orbit at the lone Lagrange point and detect objects approaching from the sunward direction. NEO Surveyor received full congressional approval and launched in 2028. When fully operational, it is expected to discover the majority of potentially hazardous asteroids to 140 meters within 10 years, including most in sun-crossing orbits. The gap is recognized and a solution is funded. But NEO Surveyor is not yet operational. The gap is open today. Any asteroid larger than 50 meters approaching Earth from the sunward direction right now could arrive with essentially no advance warning hours at most when atmospheric entry begins, not the years required to mount any deflection. The 2023 NT1 approach involved a 60-meter object. If it had struck the center of a metropolitan area, the energy release would have been approximately 64 times that of Chelyabinsk. The 2019K approach involved a 100-meter object. Its energy release would have been catastrophic at city scale. Neither was detected in time for any response. Chelyabinsk was 20 meters. It injured 1,613 people and broke glass across an area of approximately 3,600 square miles. How many 2023 NT1 class objects pass through Earth's orbital path each year without appearing in any catalog? If NEO Surveyor experiences a technical failure after launch, what is the contingency? What do the authorities actually do if we detect a 100-meter sun-crosser with 72 hours of lead time? And who is responsible for telling people? From the gap in our vision, we come to the final item, not something approaching, not something calculated, but something that has already happened, and that most people on Earth did not notice. Number 10, GRB 222-1009A. On October 9, 2022, every gamma-ray detector in space saturated simultaneously. The Fermi Gamma Ray Space Telescope, the Swift Observatory, integral, agile. Every instrument designed to measure the most energetic explosions in the universe hit its measurement ceiling at the same moment and could not record the full intensity of what it was receiving. Astronomers described it afterward as trying to drink from a fire hose with a teaspoon. The event was formally designated GRB 222-1009A. Within days, the astrophysics community gave it a different name, the Boat, the brightest of all time. It originated approximately 1.9 billion light-years away, in the constellation Sagitta, 19,000 times the diameter of the Milky Way, and it ionized Earth's atmosphere, not a planet near the source, not a theoretical extrapolation. Earth's ionosphere, the electrically charged layer of the upper atmosphere that reflects radio waves around the globe, was measurably disrupted by a gamma-ray burst from 1.9 billion light-years away. Radio monitoring stations across multiple continents recorded the anomaly. The data exists. The instruments logged it. GRB2 221009A, detected October 9th, 2022, at 13:16:59 UTC. Detected simultaneously by the Fermi Gamma Ray Space Telescope, Swift Observatory, Integral, Agile, and ground-based monitoring networks. Location: approximately 1.9 billion light-years, constellation Sagitta. Duration of primary emission: approximately 7 minutes of extraordinary brightness, followed by an afterglow tracked for months. Brightness: approximately 70 times brighter than any GRB previously recorded across more than 50 years of gamma-ray astronomy. Multiple instruments saturated the true peak flux remains unknown. Papers published in Science in November 2023 confirmed detection of ultra-high energy photons associated with the event, the highest energy photons ever linked to a gamma-ray burst. Ionospheric disturbance confirmed by anomalous behavior in low-frequency radio wave propagation recorded across multiple global monitoring stations, consistent with GRB-induced ionization. The boat disturbed Earth's ionosphere from 1.9 billion light-years away. Astrophysicists explain that GRB2 221009A, while the most extraordinary gamma-ray event ever observed, occurred at cosmological distance and posed no physical threat to Earth. The ionospheric disturbance was detectable by sensitive instruments, but biologically trivial. GRBs at this distance are a natural feature of the universe, and the probability of a similar event within the Milky Way is extremely low over human timescales. 50 years of gamma-ray astronomy have produced no event that threatened life on Earth. The boat is scientifically invaluable. It is not a threat, but the boat is something more important than a threat. It is a demonstration. From 1.9 billion light-years, 19,000 Milky Way diameters across the universe, a gamma-ray burst reached into Earth's atmosphere and measurably changed it. Not in theory, not in a simulation. Radio operators and ionospheric monitoring stations confirmed it on October 9, 2022. The post-boat analyses also required revision of standard stellar collapse models, because no existing theoretical framework predicted a GRB at this energy scale. The boat exceeded what astrophysicists believed was physically achievable, and it forces a direct comparison that cannot be ignored. WR-104, the Wolf-Rayet binary system that opened this video, sits approximately 8,000 light-years from Earth. The boat originated from 1.9 billion light-years. Radiation intensity follows an inverse square law. At 8,000 light-years rather than 1.9 billion, a boat-scale event would deliver approximately 56 billion times the energy flux that reached Earth on October 9, 2022. The ionospheric disturbance that was detectable but survivable would not be survivable. The boat is not a threat. It is a receipt. Physical proof, confirmed by instruments on multiple continents, of what these events actually do when they cross the universe and arrive here. The brightest explosion ever recorded washed across the planet on October 9, 2022. The ionosphere responded, "Nobody told you. You were going about your day." These 10 items are not assembled from speculation. They are findings from NASA, ESA, the European Southern Observatory, Nature Astronomy, and Science Journal. The reassurances are real. The monitoring programs are genuine. And WR-104 is still there, 8,000 light-years away, in the direction of Sagittarius, still rotating, still burning through its core. The BOAT showed us what the arrival looks like. Subscribe if any of this kept you up tonight. Like if you want to know what comes next. And drop a comment. Where in the world are you watching from?